and the continuation also from stream HPC. So manual AMDGCN assembly analysis and optimization. It's the stage C of it.
Yeah, sorry, this is a shortened title because I don't want to read out the full title. But yeah, hi, I'm Nara. I'll be diving in a little bit more into the more engineering aspect of working with AMD GPUs. So this is a little bit more lower level than most of the research stuff here, but I hope you'll be interested in it. So first of all, I'll be have some questions. So yeah, who knows? Oh wait, sorry, this is wrong. Yeah, I'll be talking about hip assembly and like what is it? What does it look like? I'll also be like explaining, okay, why do we want to look at the hip assembly itself? Also, like talking about like how can we optimize assembly here from a high level like programming language, and I'll be diving into some case study that I did. Also some room for questions and discussion. So yeah, first of all, some questions. Yeah, who has written a kernel with hip and CUDA here? Either hip, CUDA, okay. And who has written any assembly code, x86 or AMDGCN, PTX, whatever? Okay, yeah, not too many people, but hopefully I can explain it well enough. So usually when we write code, we write in a high level language. This can be C++, HIP, CUDA, Haskell, whatever. And so the compiler takes this code, both usually host code and device code, and we compile it down into some assembly. So for AMD GPUs, this is AMDGCN. And for CUDA, you usually compile it to PTX, and that gets down compiled to actual SAS, which then runs on the GPU. So for most GPUs, it's the same, but here we're mostly interested in the actual device code. And so this compiler here is a black box that somehow takes your like high-level program and then turns it into something that this accelerator can understand. And well, the quality of this assembly directly influences how well code runs, right? So if you have a bad compiler, then no matter how well you write your code, it will produce bad assembly, which results in bad performance. If you have a good compiler, then you can just write bad code. So this is how AMD GCN looks like. So on the left, we have a high-level representation. This is a kernel code where we read some thread identifier. We load some values from memory, and then we just write something back depending on some checked value. And this is when you compile that down. This is what it looks like. So the loads are just loading things from global memory. It does some bit shifting. It waits for data to be available. So that's the wait count, LGM CNT. We do more data loading. We wait for the data to arrive. We do our bitwise check here. So we're checking the first bit, and then we wait for our A or B value to be arriving, and then we can write that out. So that's very simple. Any questions so far here? Okay. So why do we dive in so deep into this here? Because, well, sometimes you have already all your high-level optimizations. You're already using an algorithm with a very low complexity. You already improve memory accesses, but it's still not fast enough, right? So in this case, especially if you're running into an issue where you're compute bound and not memory bound, well, you have to figure out something else. And so so this is the moment you start looking in profile tracing or the assembly here. And also, I think it's really cool and fun if you dive into the assembly because not a lot of people do it. And it also really teaches you how this compiler, which is, LLVM is not a small thing, how this compiles your code into some actual assembly that it, like, you'll start to understand more on how this entire toolchain works. And it's really not like scary and difficult at all. You just have to get used to it. So the idea here is that the compiler here, it tries out different ways to optimize your code. So you have, there are multiple ways to express the same equation, right? you can rewrite your equation in multiple ways. It still means the same thing. In a similar way, your compiler can optimize your code in different ways. So there will be different assembly representation of your, say, C++ or higher level language program. And the problem here is that there are basically infinite many ways, while some of them are obviously bad, to generate these permutations of your assembly. And there are just like hard limits on how long you can search for this optimal assembly. So the compiler has hard limits on how far it will search, or well, actually the budget of like these optimization passes. And the idea here is that if we reduce basically the complexity of your input, the compiler can spend more time reasoning about your code. And in a way here, you're actually more interested in doing some semantic optimization of your high-level code, which then results in easier work for the compiler. So how do we do this? So on AMD GPUs, there are some tools that you can use. So you can use save temps, which is all the intermediate files that the compiler will produce, or you can use LVM object dump, which also dumps like all the internals of your objects that you're building with your compiler. It also really helps if you know the instruction set architecture that you're working on. So if you're working on CPU land, just knowing what all the x86 instructions does or having the document nearby also helps. For AMD, this is the AMD like CDNA3, I say, or any other. NVIDIA probably also have something. I don't know. I don't work with NVIDIA. And also a good diff tool helps if you're comparing things. Don't use VS Code's diff, it's slow. Use something like Melt. So conceptually what we can do here is pretty easy. If we have some code that is quite optimal, for example, we gave the compiler more budget here to optimize things, or we had a good version of a compiler and suddenly it regresses, we can compare two assemblies here. And if we have two things that are very similar in behavior, but then have different performance, well, we can just look at what the code, what the generated code is, and then just revert the difference. If we find the instructions that differ here between the slow assembly and the fast assembly, we can effectively reverse engineer how that should be expressed in our high level language to result back into that optimal code. And then so we replace the code and we benchmark, and then hopefully we'll have some optimized code. So this is a case study of a time where I applied this technique with a coworker of mine. We had an 8% performance regression in a newer compiler, which was really annoying because the code was basically the same. It was like maybe like 1,000 the assembly changed. And it turns out it was occupancy related. So there are some resources used on this GPU, and suddenly, well, we're using like 10 more registers. And how the hell do you reduce 10 registers in a kernel? Well, and because of we are using now more resources on this GPU, we can parallelize this process as much because you only have limited resources available. So the goal here is to find out why it's using these extra resources and make it not use those extra resources. So we had the plan before where we just compare things and then revert it, and it should be pretty easy. So we dumped the assembly, we start comparing it, and then we realized that our kernel is like 14 megabytes in dumped assembly. Yeah, that doesn't really work. So I'm not going to scroll to 40 megabytes of data. We have some problems here. So first is how do we identify where these new registers are introduced, these resources that we're using now extra, like where do we use these? And how do we spit through this so much data? So if we look at the assembly, we actually can kind of utilize a little bit on how the compiler like allocates these registers. So these registers are usually allocated in an ascending order. And if there's something freed up, then it will reuse something. But generally, there will be this monotonic trend. So first we allocate V1, then we allocate V2, etc., etc. So here you can see, well, like we have V11. We can reuse an earlier V10 register, but we can also allocate a new register to be V12. So the idea here is when we introduce an extra load or extra allocation here, the register numbers will also tell us that. So for example, if we know that the last two instructions here are always required, right? And then suddenly there will be an instruction that basically bumps all the, this will be using an extra register on the like an extra resource, then subsequent allocations will have a higher identifier number here. So for P12 becomes P13, P20 becomes P14. And this is a property that you can abuse here. The compiler can also introduce some extra changes. There is some noise, so it's not like fully monotonic series that we can utilize, but we can still use some of it to at least reduce our search space when we are scrolling through the assembly. And so we will be trying to apply some binary search here, but unfortunately it will be a little bit manual. So yeah, so let's begin halfway through our kernel. You don't need to know the entire kernel, but this is just somewhere halfway. We'll see that, like, on the left side we have V118, and on the right side we have V120. So yeah, definitely on the right side there has been some earlier place where some extra resource allocation has been used. And so we must probably search in an earlier half, and then we start searching in the earlier half, and then we see that, well, there has been some change here, but these changes don't really change the resources here. So yeah, this is probably later here. And then so suddenly when we keep repeating this, we will find our malicious instruction here. Where, for example, this value like OX7FF8 will gets loaded in V08, V108 on the left side, and now suddenly it's V110 on the right side. So suddenly there are like extra magic values being loaded, and these require now more resources. And why is this? And these are like very weird, suspicious numbers. Like we see this is weird. So we'll try to find the this where this magic number comes from. So we'll start searching for like the V 106 and V110. Like, let's see what they're doing here. And then on the right side here, we see that V106 is being masked out here. And this previous value here, this 9908, now gets removed on the left side and becomes a register. So that is weird. So suddenly, instead, the compiler now thinks that it's more optimal to, instead of injecting the magic value directly, it will now wants to put it in a register. So what is this original code? So here we have the assembly on the right side, and on the left side we have the compiled assembly, and we basically see like, okay, well, we kind of see the idea what the compiler tries to do here. There's this a bitwise check here, which is basically a Boolean check, but then we just are interested in the first bit, and then we multiply it by matrix A to get this magic value into the magnitude of this this computation here. And on the right side, it basically does very similar things. It does a bit filled extract, and then it multiplies it with the magic number. But then instead of multiplication, it uses an AND, because now bit filled extract here basically means that we look at the first bit, set all the bits in the register to that one bit, and then we use a bitwise AND. So it's not directly multiplication, but yeah. So this right side here is the original code, by the way. But yeah, so now what we can do is basically here. This is the unoptimized the regression case, where now it does something like it basically literally takes the left code, right? So here it does something slightly different, and here it does completely different things. So, but then this is a more literal translation of the left side. So here it does literally a bitwise AND. It does a sort of comparison, and then it does a CND mask. It's actually not really exactly same, but yeah. So these two assemblies here are the same thing, but then this one uses more resources. So what we want to do here is we're basically going to fill in the blank. So how would you write the right side here into the left side? And that is quite easy. We literally do a bitroot extract and then a bitwise AND. So here we basically use same with bitwise operator to have this bitwise field extract, which is basically a ternary operator, set everything to -1 if it's 1, and otherwise set it to 0. And then we literally call bitwise AND on this magic value. And once we do this, we actually see that we are back below 128 and below register usage here. And so you can see here that the occupancy goes from 1 to 2 because we're using less registers. And yes, it works. Earlier, you also saw that there are some extra move instructions and some extra magic values introduced. So that was this OX100 here. It got removed, and then some other magic values got reintroduced. Yeah, when we check out our fixed code, it actually changed things, which is like weird, but yeah. So there's 0x100. Yeah, this basically like got moved to somewhere else when we inspected it, and well, this caused some different code here, and on the left side it was where was I? Yeah, on the left side it got it was using this OX100 code directly, and now it basically got replaced by some extra instructions. So the compiler already does some optimization here, where it basically balances some registers and instruction count. So yeah, it's not really bad, but yeah, this is some idea where you can, if you look at the right side, yeah, this could maybe be optimized a little bit more. So yeah, yeah. So for conclusion, yeah, when dealing with compiler-related regressions, you can use the assembly to basically identify like differing ways of generating the code, and you can deal with that in a way by like touching up on the higher level code. And yeah, if you reverse engineer the actual assembly, you can reduce some of the like workload of the compiler to get that better output. Yeah, yeah, this was it. Any questions?
Okay, thanks, Nara. Donnie. So thank you for the talk. How long hours would it take to get from the observation that there is a regression until you get the solution? I guess it's not a short adventure, right?
Yeah, it was. So this took about like a week, but it was also mostly teaching my coworker on how to do this. If you have everything set up properly, you can probably do this within like a few days.
Yeah, so my question is there any way to use AI to accelerate your, at least some part of the job? Because yeah, it's feeding directly 40 megabytes of assembly output is not going to work until you have access to Mythos. But basically, if you have some tools, I could imagine some harness that could at least concurrently with your other work could crunch through the output data and at least find a spot where, hey, this is the earliest point in the diff where something goes off. You need to start here looking.
Yeah. The problem with AI is that, well, first of all, it's a 40 megabyte file, so you'll be hitting your token limit quite fast. So apart from that, I would probably more look into the side of using AI to just generate a tool to search for it. Because it is somewhat monotonic. If you can already find the monotonic spaces, you probably reduce your search space quite significantly. But because it's a binary search, like 40 megabytes, we had to jump like 4 times. It's not that much because you don't have to do a full binary search on the entire file. You just look at the diffs, right? Which is much less, but then it still takes some time.
Yeah. So the question is, then I don't know which parts of the workflow are the most time-consuming ones, but the general question is, do you see value added by the large language models to aid in different parts of the process to save you time?
I haven't looked into it. I think they could help, but the most time-consuming part was actually benchmarking it.
I see. Okay, thank you.
Okay.
Thank you. Further questions or remarks?
If there are no questions, I also have 2 extra slides.
Yeah, okay. Go for the exercise, please.
Also, this is something more recently found. Which one of these 2 cases are faster? This is a trick question. They're not the same. Yeah, the left side is faster. So if you like the left side is just lower code length and it has less VGPRs. So yeah, if you're using any like AMD based GPUs, don't use condition branching. Use ternaries. That's all.
Okay. Any final comment to this? If not, let's thank Nara and also for all the morning speakers.